Hi there, so today I'd like to demonstrate doing RPM control with a brushless motor controller. So this is a standard ESC that would be used like on a model airplane, say a quadcopter. So what I have here is I have a computer that's got QBIDE on it, and this is a test fixture I made, and it has a STM32 L476 Nucleo board on it that I'm going to use. So I have a little program going on in here, and I have the motor here. I'm going to run that soon, and the battery I was going to demonstrate first and then get into the design of it a little bit. So what I'm going to do is I'm going to connect the battery first. So this is 11.1 volt battery, and you can hear the ESC play its song. And so right now I'm going to put a command in. So I'm going to put a 3000 RPM command in, and I just type it and stomp on the memory of the processor. So that's 3000. So now I'm going to put 4000 in. Now I'm going to put 5000. 6,000. Going to type 7,000. Going to type 8,000. Going to type 9,000. And the highest is 10,000. So this motor has a range of 3,000 to 10,000. So let's go back to 3,000 and see if it gets there. So I have a little algorithm, a proportional plus integral controller in there, and I'll explain it to you a little bit more. So one way I like to confirm my RPM is I have this digital tachometer. I don't know if you could see that there, and there's a little target on here, a little reflector on there. So I'm going to go run that and try to see if I can verify the speed. So I'm going to put the 3000 RPM in there by typing 3000, and it's running. And I don't know if you could see it, but sometimes it goes to 3000. It kind of drifts around. But let's see if I can get a good 3000 reading. There it is, right there. It was reading 2962. So now I'll try 5,000. So I'm getting... Sometimes it sees other things with the lights in here. We did, okay, 4916, 5,000. So it is working there. So I'm going to go back to 0, 0 will stop it. So now I'd like to show you some of the components of this test system. So I have this NUCLEO-L476RG card, and I have a servo simulator. So this puts out signals that simulates what a radio control receiver would have. So it varies from like 1 millisecond to 2 millisecond pulses, and it replicates itself every at a 50 hertz update rate. Now this thing has a 400 hertz frame time, so it's putting out those pulses, but it updates every 400 times a second. So I don't know if you could see this, but I have let's see if I can bring that up. So this is a RPM sensor that plugs into the ESC. So it taps off the 3 wires, 2 of the 3 wires. You can pick any 2 of them, go into the brushless motor, and it kind of squares up the signal, so it gives you a nice RPM, a signal that represents RPM. It gives you pulses. And then over here is I have the ESC. This is a 30 amp one. It's a Turborix. It's called Turborix is the company. And then we'll go take a look at the motor. So this is the brushless motor. It's a pretty good size motor, 1100 kV. And I have a little target on there for the RPM tachometer sensor, and this is the battery. So I'm using 11.1 volt. It's a three cell battery. It's I believe it's 2200 milliamp hour rechargeable LiPoly battery. It's also Borix is the name of the company. So the other thing I have here going to the card is a USB connector that goes to my computer. So this is the computer that I'm using, and it's a Dell Optiplex 3020. It has a i3-4130 processor in it. This is the USB cable that goes to that Nucleo board. So this is the monitor to the computer I'm using. So the nice thing, it has a Cube IDE which is running. So this is updating this. This is a thing called live expression. So you can look at parameters in the memory. So how I provide the command is I type it in here, and this is the RPM and the filtered RPM. So I'll show you how that works. So if I type in 3000, it starts moving at 3000. So this is my RPM and filter. I have a little filter on the RPM sensor, so you can see it's holding about 3000. This is the error. So I have an integral and a proportional part in this control loop that I'm going to go through. And if I want to go to 4000 RPM, it locks into 4000. If I go to 5000, it locks into 5000. If I go to 0, the motor pretty much stops. It has a range from about 3,000 to 10,000 RPM. Now the reason why I would do it this way is I want to control the power to my motor. Since I work with a lot of quadcopters, I have all 4 of them running at the same time. So rather than just be open loop and giving it a command, it's hard to balance the motors. So if I could give it an RPM command, which is proportional to power, RPM times torque is power, I could balance the power between the 4 rotors of a quadcopter or 6 rotors of a hexcopter. So that makes it much easier to control, makes it much more stable. If I didn't do that, it would be very hard to stabilize the air vehicle. So this is a good way to control the RPM of a brushless motor to help stabilize a quadcopter. I can never get it to fly if I just gave it straight commands without feeding back RPM. So anyway, we'll go and look at that algorithm a little bit. Okay, so I'm going to talk about this RPM controller for like a brushless motor that might be used on a radio-controlled aircraft. So the board I'm using is this NUCLEO-L476RG that you could buy off of DigiKey or a lot of other places. It was relatively inexpensive, might be somewhat outdated. So I'm using Cube IDE version 1.10.0, and this is it's really good now because it's all free, and it has Cube MX built into it that allows you to set it up real nice. So the NUCLEO-L476RG has 80 megahertz clock. So it's a relatively slow, low-powered processor. I wouldn't recommend it for like a radio-controlled or like a quadcopter quite yet. It's a smaller processor. You need something that's bigger. But for just controlling one motor, it's a good way to go. So this technology is really great now because if you're a hobbyist, it doesn't cost much. And it gives you very good deterministic frames that you could use to control an aircraft. So I'm doing... what I have in this system is I have a 400 hertz frame rate, and I'm using timer 3 to provide an interrupt. It's a software timer that's built into the processor, so the timer counts a certain value. When it hits that value, it sends an interrupt to restart it 400 times a second, so that I get real nice deterministic frames. So this goes into the motor. It's a bigger motor than I'm used to working with, so I'm pretty sure you have to customize all your parameters around your motor and your ESC. And I didn't use a programming card for my ESC. It's just one with the default values in it, so I didn't try to change the settings on it. It's a model FM30A ESC. So the thing you also need is this little RPM sensor that kind of squares up the waveform that allows you to read the pulses. So the faster that motor turns, the smaller the pulses. That tells you it's proportional to RPM. So you measure the pulse. I use another timer to measure the pulse and use that to compute the RPM. So this is when you buy the Nucleo card. I believe this probably costs me under $20. The STM32 L476. This is the pinouts that they give you, and it was part of the packaging that came with that card. Okay, so I have some of the connections here. So I have a servo simulator. So the servo simulator is it was a little device that had a knob in it, and when you turn it, it simulates kind of the output of a receiver, like a radio control receiver. So it sends pulses. It varies from 1 millisecond to 2 milliseconds, and 1 millisecond means, say, 0%, and 2 milliseconds means 100% command. And so I have a little switch where I could connect that directly into the ESC, so I could simulate it in more of an analog way. So anyway, here's a picture of the test rig I made, and this is the servo simulator. I just wanted to show you. You could buy these off of eBay, I believe, for a very cheap price. And I have some switch. I don't believe you could see the switch in there, but I have a way of switching it directly to the ESC where I could switch the output of this to the ESC. So I could either drive the ESC using the servo simulator or using this Nucleo board. So we were talking about the servo simulator, so I also have that connected to the Nucleo board, and I was just going to use that to read the knob position, so I could put like more of a knob type analog command into it, so I could vary the RPM that way also. So that was the purpose of that, and also to run the ESC, I could switch that in for test purposes. So I used timer 15 to read the pulses off the servo simulator. So it has a normal range of 1 to 2 millisecond pulses, which translates to 1,000 to 2,000 counts. And I put in there, yeah, it can be used to drive the ESC, the electronic servo controller, directly, or used as an input to the NUCLEO-L476RG card. And in terms, that could be used to drive the ESC. So I also have connections from the ESC to the NUCLEO-L476RG card, and I was using the Nucleo card to. It has a pulse width modulation generation feature, and I was using timer 4, so I have that connected to the ESC. Now I have there's also 3 other channels reserved for future use. So when I do make a quadcopter out of this, I'll be able to drive the other 3 motors. So I just have them reserved for future use. So I have some information on how I set the timers in there, and it's set up so 2,000 counts equals 1 millisecond. So the ESC also has a 1 to 2 millisecond pulse range. And I took some data, the counts versus RPM. Now this wasn't using that tachometer. I did it. I had previously scaled the RPM sensor in there. So when I give it 2,200 counts, I was reading 2722 RPM. And the maximum I gave it was 2,900 counts. And that gave me 10,219 RPM. So I was trying to characterize the ESC and the motor. Like if I commanded certain counts, it would give me a certain pulse going into the ESC, which gave me a certain RPM. So I believe like every motor is going to be a little bit different, and every ESC combination is going to be a little different depending on the settings. And so it's good to, you want to get this data first. So this is my connections between the RPM sensor to the NUCLEO-L476RG. So again, I'm using timer 1 So you need to have a microcontroller that has a lot of timers. I'm looking for some improvements if they make ones that have more and more timers, because everything is done with timers these days. So they kind of run, it's a good way of doing it. They run in the background so they don't hold up the processor. They go directly to memory. So it's a very good way when you're doing microcontrollers is to use pulses. So anyway, this isn't the servo simulator. Got to correct this. This is the RPM sensor. So I made a little correction there. So timer 1 is used. So the pulse is scaled for 1 microsecond per count. So I did use that tachometer, and it was found that I was reading 2567 RPM when the pulse was at 1.68 milliseconds. So I was able to develop a scale factor. So it was found to be 4.31256 RPM second. So to compute the RPM, take 4.31256 and divide that by 0.00168. That comes at matches at 2567 that I measured on the tachometer. So a DT2254C plus digital tachometer was used to verify the scaling, and those are very inexpensive, probably not more than $20. I bought it, I believe, off of eBay. And this is a picture of the test system. So here's a close-up picture of the motor, Outrunner brushless motor, used in the radio control model airplane industry. And this is the label that was on the other side of the motor, and you can see the 3 wires that come out of this motor. So this is the ESC I was using, the electronic speed controller. I call it electronic servo controller sometimes for brushless motor, and it's programmable. I do have the programming card for it, but I just left it at its default factory settings. And this is the little RPM sensor that's very light that reads off 2 of these wires. So this waveform, if you ever look at it, is very noisy. It looks more like a sine wave sometimes. So this somehow takes it and squares it up. It makes it nice, good looking. So I don't have to make my own electronics for this. So it's these are a few dollars. So it's worth the price to buy one of these to get RPM. So here's the battery that I was using. I believe this battery is somewhat dead because it never fully charges. It's pretty old. It's getting a little puffy, but it's good enough for my lab use. Rather than put it on an aircraft, a radio controlled aircraft that I could damage. So I think this is at its end of life, this battery, but it's good enough for lab use. So here's the manual that came with the RPM sensor, and it doesn't really give you enough information to figure it out. So you basically have to reverse engineer it yourself. Yeah, I like this RPM range, 1,000 RPM to 300,000 RPM. Boy, I like to see one of those motors run at 3,000 RPM. I don't know if anything like that exists. So this shows you the connections you need for this RPM sensor. It's pretty simple. So the next thing I have the manual for the brushless motor controller, and these are the typical ones. I tried building some of these myself, but to make them that small, it's impossible. That small and light, so it's best to buy one of these. Buy them. I believe they're all made in China, and they do a good job on them, and they seem pretty reliable. I just went with the factory settings. I didn't do anything to do soft startup or break on or break off. Whatever the default factory settings were, that's what I went with. So here's some more information that came with the brushless motor controller. So what I did is I made an Excel spreadsheet of the RPM profile counts. This is counts going to the ESC. So 2,000 is equivalent to 1 millisecond. So 3,000 would be equivalent to 1.5 milliseconds. So it doesn't go over 1.5 milliseconds, although in the radio control industry, 2 milliseconds would be considered 100%, so they really only go up to about 50% on this, on the scaling. But anyway, so nothing happens until you hit above 2000, and then it has this profile. It's kind of like a non-linear, it's not a linear profile. In this area, you get the most RPM change, and as you go higher, it levels off. So, but with this RPM controller, it makes it nice and linear. So that's the problem you have if you just give these motors the 1 to 2 millisecond input. You know, you could be any place on this curve, and it's very difficult to control. So I don't ever recommend controlling a quadcopter. Maybe a radio control single propeller airplane would be okay to do it without RPM control, but if you're doing a quadcopter, yeah, you definitely want to control the RPM. So the magic thing here, lastly, I wanted to show you is the control loop. So I'm using the proportional and integral path control. So I put this spreadsheet in here. It represents that motor, the characteristics of that motor, the ESC motor. So this is RPM in, and it's not RPM in, it's counts in and RPM out. So it has this profile. So when I put the counts in to the ESC, it generates a RPM. So I noticed the RPM sensor is a little bit noisy with the timer. So I put a filter in there. This is like a low pass filter with a bandwidth of about 31 hertz. I use it's a digital filter done inside the microcontroller. So I have a filter version of RPM just to try to take out some of the noise. And I was trying to get this error to be low. So I was trying to keep it under maybe 20 or 30 RPM, this error. So this is the RPM command. So it could vary from 3,000 to 10,000. Anything below 3,000, the motor doesn't turn. The motor won't run. And once you get to the higher RPM, the 10,000, it kind of levels off. You can put more counts in, and it stops. So there's a little proportional part, and the main path, the main important thing is this integral path. So this integrator will keep integrating until the error is close to 0. So it's trying to regulate this error to be 0, the error between the RPM and the command. So to keep it stable, the proportional part is important. I didn't try any derivative control. The other important thing is to put this bias in. I put the bias, which gets you to the 1 millisecond, the 2000 counts, and the scaling I was using gets you to 1 millisecond. So that's the bias, and then so it tries to control it within this range. So anyway, this is the main thing, the integral path. The gain I used was 1 here, and the proportional part is 0.2. So this takes the RPM. It's in floating point, so it takes the RPM and multiplies it by 0.2, so it generates 0.2 counts per every RPM. And this integral, actually it's a limited integrator. I limit it to plus or minus 2,000 counts. And so it's just a gain of 1 count per second RPM. So I tried different gains. If you do make this higher, yeah, it starts getting a little bit unstable. So I haven't done a stability analysis on it. I know the dynamics of the motor has about a 0.1 second lag, so there should really be, I don't have the lag modeled in here, but it's about a 0.1 second lag. So, but anyway, by trial and error, I was able to vary these gains and come up with a somewhat optimal design for this. So anyway, if you ever have to do RPM control on a brushless motor for like a radio-controlled airplane or a quadcopter or eVTOL or anything, this might be a good way to do it. So thanks for watching this now. Bye now.